Okay, so now let's talk about how a combination of bottom-up and top-down neural networks can be trained. So in this case, basically, let's assume that you have a bottom-up network, and then you have a top-down network. Okay, so I will call the bottom-up network as a feed forward network, and I'll call the backward network as a feedback network, similar to what Timothy Lillicrap talked about in his paper. So in the feed forward path, what will happen is that you feed in X and you get the input activities H1, H2, H3, and then you can train like a backward neural network in such a way that it takes like these output activities and gets like this H2, H1 dash, and similarly like output X back, and then you can compute like this sort of local errors, which is like H2 minus H2 dash, and you can compute like how much error this backward network is making, this WB network is making, and then you can update like the weights of WB in that way. So you can calculate like you can make a single forward pass which is like top down, bottom up, and then so this is like the single forward pass you make in bottom up, and then a single backward pass using top down network. You can compute their hidden states, and you can compute like the L2 norm between them, and you can like update the weights of like the backward network in this way. So this is like talking about how will you update like the weights of like the backward network. And similarly, there is another way, like how do you actually train the weights of like the forward network. So there has to be like a way to train like the forward network also, and there are two ways in which you can train such a forward network. Let me talk about the first way. The first way is that, let's say that you fed like a so let me just clear up the screen so that the second way becomes like a little bit more clear. um, Okay, so let's say that we want to train this feed forward network. So let's say that you fed an input X, and finally like whatever activity you got is H3. Okay, and now like the key point is that there is like a correct answer, there is a correct activity which is H3 dash. This is like the correct activity which your network should output in case it is doing a perfect job, and you can easily pass this sort of like correct activity through like a top-down neural network, which is essentially trying to tell the neural network, hey, this is the activity at the top layer which is the perfect one, and I am going to use a neural network which will actually predict like what will be the perfect activity at each layer, in case like the network did a perfect job of learning like the intermediate representation. So here you are not computing the gradients, but you are using a network which is actually predicting the activity from the top part of the network to like the bottom part. So let's say this H3 tilde is like the correct output. So like in case like your output neurons in case like your outputs, you're doing a regression, and then your output layer has like 3 neurons, then you know like the precise value 1.0, 2.0, and 3.0, like whatever your neural network should take. So that is H3 tilde, and once you transform it by using like a top-down neural network, essentially it should give you like a correct estimate of like what the correct hidden activities should look like. Okay, and then the key point is like you do this training, and then you optimize like the weight of your forward neural network. So in this case, like while you are doing like the forward neural network, what you want to do is you want the error to be low, like whatever you use between using like the top down connection, and then this is like the correct activity which your neural network should output. So from the perspective of like the forward encoder, there are two things you are doing. One is that you're telling this H2 that what should be the correct activity which it should predict in order to get the perfect answer, and you can construct that by using like the activity of like the correct outputs and just propagating them. So you can tell H2 that it needs to be similar to the activity which the top down neural network will get after you fed like the H3, when after you fed like the correct activity H3 tilde to it. Okay, so that's like one of the key ways. And then there is like this term which is known as this error correction term, and what it is essentially doing is it's telling the forward neural network that, hey, if you fed in X, then whatever output you get, if you feed that output to the top down neural network, then you should get the same answer. So you need to understand that there is a difference between these two paths here. So there is like one path which is in this way, this blue path, And what's it's like it's not involving the correct error, it's not involving the correct signal. So this is an unsupervised phase in which like you fed like the output of the top activity back and you compute it like the intermediate activity h2 tilde, and in this case you're telling the network whatever you fed as input should be actually the correct one in the output. Okay, and that's like what you can do. So you can train like this h2 and h2 dash, and this is like the correct error. And then so this error should be like very low whatever you get. And then similarly like the this is like the correct error signal which like your which you get like from the top down neural network, and that's how you compute like the activity which is the current activity. And you can like then create like you can create like a you can update like your hidden activity in that way, and you can update the weights of the neural network to essentially minimize like these activities. Okay, uh, okay, so that's good. So you want to like make this whole thing to be zero, and similarly you want this thing to be correct. Okay, and now the key point is how do you train like your top. So this is how you train your forward facing neural network, which is this wf. You try to reconstruct the activity which it went in, and then you also try to reconstruct the activity which is essentially the correct activity for a given set of like training and testing examples. And then your final activity is like a sum of these two activities. So we have discussed how to train like the forward facing network, like the bottom up network, but how do you actually train like the top down neural network? So this was only holding true for like the bottom up neural network. So let's try to train like the top down neural network. And training the top down neural network is like a different kind of story, but it's essentially very intuitive. So what it is saying is that let's say you have like a forward facing network, and you fed it like xi and you got yi. Now when you feed it yi again, it should give back xi. So then you can apply like a L2 loss on this, and you can create a gradient. So you can take like gradients over wb, and it will allow you to update like the top down neural network also. And the key point is that if you fluctuate like your input like by a certain amount epsilon, then what will happen is the output activity will change, and then the whatever activity was changed by the epsilon should essentially result in the same amount of perturbation which you made to the input. Okay, so let's say you have like a forward facing network, you have x, and then it gave you y. Now you applied epsilon 1 here and you got epsilon 2 perturbation as output. So essentially you can take like y plus epsilon 2 back, and you should be reconstructing x plus epsilon 2. Okay, so now your learning algorithm can consist of like two phases. One is like in which you're training like the forward, in which you're training like the forward facing neural network, like the bottom up neural network. And then in another phase, you're training like your top down neural network. And that's essentially like what you're doing. So this whole thing is known as like a this whole thing is known as a like very fundamental problem, and there is always a issue of collapse. So the issue of collapse is that whatever your networks learn, they will learn the weights in such a way that they will always output the same thing. So for example, when you are trying to like do this kind of learning between alternating between the phases of forward neural network and a backward neural network, there is a condition when forward neural network and backward neural network can be zero. And if they are zero, then essentially what happens, whatever you input will be the output, and then that output will still be the input. So like if zero goes in, zero comes out. And so if you send zero in, zero comes out. If because if your weight is zero, then whatever you send in xi will become zero. And then from this zero, like you can essentially never get back the signal which you sent in xi. Okay, so like there are like these stupid loops in which like this is known as collapse. So this is known as a collapse problem, and sometimes like the neural networks are not able to function well in this scenario. And obviously that's why like till now a lot of people have not been able to train this kind of like bottom up and top down neural networks. And this approach in which like you're taking your forward facing neural network and you're fluctuating your input by like a certain amount, and then your network gets like yi plus this, and then you are trying to like train like a top down neural network to get back like the input signal, is essentially telling that you are essentially trying to predict like what was the noise which you added to the input, right? So you're trying to predict x plus epsilon, and obviously you can imagine that you are adding like several kind of noises, x plus epsilon 1, x plus epsilon 2, x plus epsilon 3, and so on, and your network is trying to predict like epsilon 1, epsilon 2, epsilon 3. The top down network is trying to predict that every time. So since it's trying to predict like the very noise which you added to the input neural network to the bottom up neural network, so this kind of learning is actually known as denoising autoencoder, and that is like the same concept which people have used in diffusion models, but there like the math is different. But that's essentially the same idea, that you learn like this, you learn this denoiser which tells you that if input is changed by a certain way, what then it predicts like, okay, what change was made in the input. Okay, so that's essentially the kind of denoising training which Hinton is talking about in his other paper called glom, which I will cover later. But that's it for how you train like the forward and backward neural networks. So to recall, forward equation is given by this, in which like you have a error correction term and you're trying to predict the correct signal which your neural network is predicting from the correct outputs. And then similarly, the bottom up is trained as a denoising autoencoder, where like you fluctuate the input a little bit and then you get the correct answer as output. So that's all. And as you can see, this algorithm does not involve any chain rule, and it does not involve like any sort of knowing f dash, and it also does not involve storing like xi, yi, and zi in memory. And now let me talk about like how does it look like if you want to train like several layers of a neural network using this algorithm. And that's a pretty cool idea. So here, like as you can see that you will go in forward phases, and what will happen is that you will still store h2, h3, and h1 in memory while you're training this thing. But then once you like learn to approximate this, then essentially you have like you have learned this perfect top down neural network, and in that case like you don't need to store these activities anymore. So that's a really good thing, and that's what is the benefit of target propagation.